Okay, in this video, I'm just going to go through a answer key for the worksheet that's associated with exam 3. Okay, there's also a hard copy of the answer key as well, but I just want to discuss a few of the issues that arise after grading a few of the problem sets. All right, okay, so this is a synthetic conversion problem, part 1. So all that's required here is that we design synthetic routes to produce each of these compounds. We don't have to write mechanisms or anything like that. Some of these are one-step transformations, and some of them are multi-step transformations. But look at the directions here, and you can sort of get an idea for what's going on here. Okay, so let's just look at some of the issues here. Okay, so hint number 1 is that there's a designated starting material. Okay, and the designated starting material is this compound, parabromoethylbenzene. Okay. So this is going to be the ultimate starting material for everything here. Okay, so what does this mean? So let's look at the hints here. We note that the conversion there to there is going to be a one-step transformation. Okay, it also tells us that this one is going to come from this one, and it's going to turn into that. And it's also going to turn into that. So take the hints given in here to help make the problem a little more manageable. Okay, so let's look at this first transformation. How are we going to turn the ethyl group into a carboxylic acid? This is just a side chain oxidation. Okay, and that's typically accomplished with sodium dichromate, aqueous sulfuric acid, and heat. Or we can employ potassium permanganate and heat too, okay? And this is done in aqueous solution, so we'll say water is also an essential ingredient for that. So that's the only one-step transformation. Okay, let's look at how we're going to turn this compound into this compound now. What you see here is that we have the 2 carbons we need. Okay, there's 2 carbons on the side chain. There's 2 carbons right there. All we need to do is we need to turn the ethyl group into an alkenyl group. Okay, and that represents an oxidation reaction. There's one thing in the book that tells you can use zinc oxide at 500 degrees, but that's really kind of the industrial scale synthesis. That's not a generally practical way to do this. The best way to do this is a 2-step transformation. Okay, where we're going to introduce a bromine. Okay, and this is going to make this compound. Okay. All right, and this is NBS, which is a reagent for accomplishing a free radical bromination. It's more useful than bromine because it serves as kind of a source of bromine at low concentration. So it's preferred over bromine itself. And once you do this to turn it into this compound here, you just do an E2 and a good reagent for that. We'll just say is sodium ethoxide and ethanol. Okay, so this is secondary. So the reaction with sodium ethoxide and ethanol is going to prefer the E2 over the SN2 reaction. Okay, All right. One thing that we can probably see also here is, well, let's just go to the next slide here, and we'll do one of the other ones. Okay, so now that we have the synthesis of this compound, which I'll just call B, in hand, we're going to see how it converts into each of the other ones. All right, so let's advance this. All right, so let's put these names up here again. All right, so we know how to make B. Let's turn B into C, D, and E. Okay, so B into C. Let's think about that one first. This is actually a one-step transformation. It's not in the area we're looking at now. This is just a reaction out of Chapter 6. We're just going to treat it first with ozone, and then zinc and H3O+. All right, so a more advanced synthesis problem is converting B into D. Okay, so let's think about how we would accomplish this conversion now. All right, so what we note here is that we have 2 more carbons in our molecule, and our directions say that we have to use sodium acetylide as the source of the extra carbons, okay? All right, so how do we incorporate these 2 extra carbons, okay? These get added via an SN2 reaction. Okay, so we need a primary halide or tosylate as our ultimate precursor. So let's just think about how we're going to turn this into a halide. Okay, so we need to turn B into a primary halide or tosylate. Okay, and key here is to do an anti-Markovnikov addition. So we're going to treat this with okay, sorry if everything it doesn't make if my writing's not good enough here. I don't have my drawing pad. Okay, all right. So we're going to do the anti-Markovnikov addition. Okay, we're going to turn this into the tosylate. This is pyridine, sorry. Okay, and this is going to give us the tosylate. Okay, and let's just remember this compound for the next slide because I've run out of room here, but we're going to see that D and E kind of come from a common place. So we're going to continue this on the next slide, but our objective here, remember, is we're trying to synthesize D and E. Okay, so let's just remember that. We're trying to convert this into this compound and this compound. Okay, so in the previous slide, we saw how we were going to prepare this compound. Okay, and now we have something that can react with our designated source of the extra carbons. Okay, and just this SN2 reaction here will do this. And you recognize that all we have to do now is turn the alkyne into an alkene. And this is, we'll just try H2 and Lindlar's catalyst. And this is going to turn that into that compound right there. Okay, so that's our synthesis of this compound. Now it turns out that this compound here is also going to be our source of the last compound, compound E. Recognize that we have these 2 extra carbons here that are also going to come from the acetylene. Okay, and in chapters 9, 10, and 11, we really only see one reaction that makes the C double bond O group, and that is alkyne hydration, right? And in alkyne hydration, we just take a terminal alkyne, treat it with water, mercuric sulfate, and sulfuric acid, and that converts this to the methyl ketone via the enol intermediate, okay? All right, so all we have to do here now is just take that compound and treat it with water, sulfuric acid, and mercuric sulfate, or mercuric acetate, either one, and that will finish that transformation right there. Okay, all right, so let's look at the next problem here, and we're going to classify each of these as aromatic, non-aromatic, or anti-aromatic. Okay, so aromatic, remember, we'll have 4n plus 2 pi electrons in complete cyclic conjugation. Anti-aromatic, we'll have 4n pi electrons, also in complete cyclic conjugation, and non-aromatic, we usually have some sort of interruption in the conjugation. Okay, it's not going to be completely conjugated. Okay, we also need to be cognizant of the fact that our conjugation can, as long as we have p orbitals overlapping with other p orbitals, we can have conjugation. So the conjugation can come from pi bonds, can come from lone pairs, and it can come from empty p orbitals. All right, so let's look at these 5 examples here. What we see here is that we have something that's interrupting the conjugation, so this can't be aromatic or anti-aromatic. We're going to call this one non-aromatic. All right, this one, remember that our nitrogen will have a lone pair. Okay, sorry, I can't really draw really good lone pairs there, but what we're going to see here is that if you count up the electrons, there's 2 here, or count up the pi electrons, 2 there, 2 there in the lone pair, there's 6 pi electrons. The conjugation is complete all the way around the ring, therefore we're going to call this one aromatic. Okay, here, boron has an empty p orbital. It's isoelectronic with a carbocation. Nitrogen will have a lone pair. Okay, so we do have complete cyclic conjugation. We've got a p orbital at every atom in a cyclic arrangement here. Okay, we have 2 here from that pi bond, 2 here, 0 there, and 2 here, so we have 6 pi electrons. And we're going to call this one also aromatic. Okay, here we have an empty p orbital for a carbocation. Here we have 2 lone pairs, but we can only conjugate one of them. Okay, so we have 2 electrons there, 2 electrons there, 0 there, 2 there, so we add them up, 2, 4, 6. This also has 6 pi electrons, and thus this is aromatic as well. Okay, all right, and this one is kind of interesting. Here we have 4 pi electrons in complete conjugation. We're going to call it anti-aromatic. Okay, that's one way to look at it. We can also look at it as a further conjugated system. And what you see here is that if we look at it being totally going around the ring this way, there's 2. Let's just count them up. 1, 2, 3, 4, 5, 6 pi bonds in complete cyclic conjugation. This gives us 12 electrons. That's a 4n number. And if you look at it this way, it's also anti-aromatic. So however you look at it, it's anti-aromatic. So this last one we're going to refer to as being an anti-aromatic compound. Okay. All right, so let's look at the next problem. Okay, and the next problem, okay, it's a HOMO-LUMO problem, and we have 3 versions of this problem. Okay, so what we're looking at is we're looking at placing all of the pi electrons in the following molecule into the correct orbitals, which means we're going to place them into the lowest energy orbitals first, and we're going to place them 2 at a time. We can't have more than 2 electrons spin paired in any orbital. Okay, so what we're looking at is the pi electrons, and we're putting them in to the correct places. That's the first task that we're going to do. All right, so for this compound right here, we can see that we have 4 double bonds in conjugation. Each of those double bonds has 2 electrons, so we have 8 pi electrons in conjugation here. All right, so we're going to fill 2 at a time till we get 8. 2, 4, 6, 8. So there's the electrons in the neutral compound right there. All right. HOMO stands for highest occupied molecular orbital. So what's the highest energy orbital that's occupied? It's number 4. So that's the HOMO. LUMO means lowest energy unoccupied molecular orbital. Okay, so the unoccupied molecular orbitals are 5, 6, 7, and 8. 5 is the lowest in energy. We're going to refer to that as being our LUMO. All right, so there's that one, okay? yeah, so this problem should be the easiest problem in the book, but a lot of people didn't really know, or a lot of the easiest problem on this problem set, but a lot of people didn't know where to start. Okay, so we're going to look at this one. Okay, so it tells us here that we're going to assume that the carbanions are sp2 with the lone pair in a p orbital. Okay, so thus the lone pair electrons are going to be conjugating. They're going to be part of the pi system. Okay, so this one is going to be focused on the dianion right here. All right, so if you look at how many pi electrons we have 3 alkenes. They're contributing 2 each. We have 2 lone pairs. They also contribute 2 each. All right, so if we add these numbers up, we come up with 10 pi electrons. Okay, so let's put 10 in the right places. There's 2, 4, 6, 8, 10. All right, so that must mean that this is the HOMO, because it's the highest energy of the occupied, so we're going to say that this is number 5. And that number 6 is the one immediately above it. 6, 7, and 8 are unoccupied, but 6 is the lowest energy of those, so that's the LUMO. Okay, so that's number 6. All right, and we're going to do it for the dication. Okay, so this is for the dication. So the p orbitals of the carbocation are going to overlap or conjugate with the alkene pi bonds. Okay, so if we look at this one, we have 3 alkenes. Each of those is going to contribute 2, and 2 MTPs. They're going to obviously contribute 0, so our total here is 6 pi electrons. Okay, so let's put them in. 2, 4, 6. That means this is the HOMO, and that this orbital here is now the LUMO. Okay, so LUMO is number 4, HOMO is number 3. Okay, all right, so the principles are: count the number of electrons in conjugation, put them in the lowest energy orbitals first, 2 at a time. The HOMO is the highest orbital that has some electrons in it, and the LUMO is the lowest energy orbital that doesn't have any electrons in it. Okay? All right, let's look at this one. We're going to write a mechanism for this transformation, and we're going to illustrate the mechanism with H+. This is just a carbocation rearrangement problem, but it's resulting in an aromatic compound, so it's a little bit more favorable from some that we've already seen. All right, so this is going to start off just like any other reaction of an alcohol with strong acid. We're going to protonate the alcohol. Okay, and this is going to generate our first intermediate. going to lose water. This is going to give us a carbocation. Okay, we know that carbocations rearrange, but it's not immediately obvious here how this rearranges because the carbocation's not directly beside where the group that's moving, but actually it turns out that it is via resonance. Okay, so we have this resonance structure here that we can write. And now you see that our carbocation actually is, sorry, I didn't mean for it to be there. I've got it kind of messed up here. Let's see. Let me see if I can get to an eraser. Okay. All right, so let's redraw that. Okay. All right, so here is the actual resonance structure. Sorry about that. All right. Okay, now as this resonance structure here, you can sort of see how we're now going to do the 1,2 alkyl shift. All right, and this is going to give us this carbocation. All right, and finally we're going to just lose that extra hydrogen, and that gives us the final product. Okay, so you need to show this protonated alcohol, you need to show the first carbocation in its resonance form, you need to show the ring expanded carbocation. Oops, sorry, I didn't draw the right ring size there. Okay, so let's put that, let me modify that last one. Yeah, so it, remember 1, 2, 3, 4, 1, 2, 3, 4. Yeah, so we have to account for the all the carbons, so I didn't in my initial picture, so now it's right. And you need to show the ring expanded carbocation and its loss of the extra proton to produce the aromatic system. Okay. Finally, let's predict the 1,2 and 1,4 addition products from the following reaction. All right, so recognize that there are two ways for this compound to undergo protonation initially. All right, so we're going to look at protonation of the right side alkene. Okay, and that gives us this carbocation. Okay. All right, so we have two hydrogens here now. Okay. All right, and this carbocation, you see, is a allylic, so it's going to have a resonance form that we can write. And this is this structure right here. Okay, we can also protonate the other alkene group. And this gives us initially this carbocation right here. It's also an allylic carbocation. Okay, and we can write resonance structures for any allylic carbocation. Okay, so now you notice that we have four distinct resonance structures. Our actual compounds are the compounds that come from just adding bromine to each of these resonance forms, okay? So we're going to have bromine here. We'll just have it add to the carbocation. So one of our final products is going to be that. One of our final products is going to be this one. Okay, and that's the 1,4 addition product from this resonance form. This is the 1,2 addition product. Okay, I'm going to kind of run out of room to write the last one. I'll try to work it in, but adding bromine to this one gives us this compound. This is our 1,2 product from adding hydrogen to that end of the dying system. And this one is the compound that you see here. Okay, so this is, yeah, sorry, I'm running out of room to write there. There's bromine, and this is our 1,4 product. Okay, but what you see here is that every product is an allylic bromide. Bromine is allylic, or the carbon-bromine bond is allylic relative to the alkene. It's true in the 1,2 addition product there. It's true in the 1,4 addition product there, and the 1,2 addition product there, and the 1,4 addition product there. Every one of these should be an allylic bromide. Okay, so that's the end